Welcome back. Let's continue the session. Right? Now, let's see other observations. What is our voltage gain? Let us say mod AV, that is what is only magnitude part. Okay. If I take only magnitude, therefore, tell me what is AV? $400, and what is mod AI? That is 40. Right? Tell me, having voltage gain from single stage amplifier 400 is high or low? Is high or low? Remember, our overall observations, finally we are trying to get the ideal amplifier, basically op-amp, operational amplifier. We want to get everything very high, whatever you want. I want voltage gain infinity, I want current gain infinity. Therefore, whatever I want which is beneficial to me, I want those things. But practically, are we getting or not? That is important, right? Therefore, can I say, is voltage gain 400 very high? Okay, then let me ask you. Definitely, maybe if you want to improve, you can improve voltage gain from single stage amplifier, maybe 400 to 500 or 600. But we cannot get 400 to 40,000. We cannot get that much, right? Therefore, surely single stage gain or having 400, maybe a single stage amplifier, that is not enough to get huge gain. Definitely we need two stages. When you take two stages, then tell me, single stage gain 400, and if you take one more stage, 400 into 400, multi-stage amplifier, right? Therefore, when you take multi-stage configuration, let us say this is what is stage 1, this is stage 1, and output of that is connected to next stage. This is stage 2. This is also CE amplifier, and this is also CE amplifier, let us say. Then whatever voltage gain you have from stage 1, let us say that is AV1, and whatever voltage gain you have from stage 2, AV2, and overall if you ask me the voltage gain, that is nothing but AV1 into AV2. That is what is your overall gain, right? Now if you say that, tell me what is the voltage gain. Let us say 400, 400. Let us say both are having 400, 400. Okay? Then 400 into 400. What is that? What is 400 into 400? 40,000. 40,000. 400 into 400. How much? 400 into 400. 400 4 is 16. 4 zeros. 1, 2, 3, 4. Means it is basically 1,60,000. 1,60,000. People take it as infinity. When I say voltage gain 1,60,000, you can take it as infinity, right? See, if you take IC741 op-amp, IC741 op-amp, if you ask me your open loop gain, open loop differential gain, I'll explain what is the differential gain and all later on. But if you see, this is what is comparable to voltage gain what we are seeing now. Therefore, AD is equal to 2 into 10 to the power of 5. Basically 2 lakhs. If you convert into dB, this is nothing but 106 dB. Therefore, if you take IC741 op-amp, the voltage gain which we treat infinity, right? When you say op-amp having gain infinity, but it is not infinity, it is 2 lakhs. We are treating 2 lakhs as infinity. But if you consider single stage amplifier, whatever we had seen till now, that is what is giving 400. But with respect to 2 lakhs, 400 is nothing. But remember that single stage gain 400 is responsible to have two stage gain or multi-stage gain, which is 1,60,000. Therefore, having single stage gain 400, you can consider it as good gain, because that is responsible when you take two stages, which is giving significant gain, which is 1,60,000. Right? To enhance that, if I take voltage gain, single stage voltage gain 100, then what will be overall gain? 100 into 100, 10,000. If 100 into 100, 10,000, then 10,000 versus 1,60,000. There is a significant change. Therefore, having single stage gain 400, 500, then people treat it as having good voltage gain. Okay? Okay. Now I can say your common emitter amplifier is having good voltage gain. Right? Now, coming back to current gain. Is current gain high or low? Don't compare or never compare with voltage gain, because you may say that voltage gain is 400, current gain is simply 40. No, voltage gain is different, current gain is different. Let me give you a small example, a practical example. Remember, whatever power supply you are getting, right, to our home applications, right, 230 volt RMS. Therefore, that is nothing but AC signal which is 230 volt RMS. But let us say that is what you are giving to fan. Then the fan is the one which is what? Let us say 80 watt fan. When I say 80 watt fan, we are giving 230 volt RMS, then the current what it takes to get the power, mechanical power, which is 80 watt, is in the order of what? Less than 1 ampere, right? It will be in the order of 0.4 ampere. Your current will be in the order of 0.4 ampere, 0.3 ampere, but the voltage will be AC voltage. If you see, that is what is in the order of 230 volt RMS, 200 volt, 200 volt, 230 volt, 240 volt, 220 volt, right? Then don't or never compare voltage gain to current gain. Your current gain, what is the meaning of current gain 40? Let us say the input current is 10 microampere. If input current is 10 microampere, then 40 into 10 micro, which is 400 micro or 0.4 milliampere, you are driving to your load. Remember, having single stage gain 40, or if you take multi-stage, it will have AI1, it will have AI2, then overall gain. Therefore, if I say this is what is having gain of AI1 and this is what is having gain of AI2, then what is your current gain? Your current gain will be AI1 into AI2. Why? Whatever current you are pumping here, 40 times of or AI1 times of, that current is the one which you are pumping into second stage, because for the stage 1, stage 2 is the load. Therefore, whatever current which you are getting from stage 1, that is entering into stage 2. Whatever current which is entering into stage 2, again 40 times of that you will see, and you are going to connect load here, then 40 times of that, which is what is entering into stage 2 input, will be given to your load. Overall, if you speak with respect to the input to output, then overall, if you say 40 into 40, which is nothing but 40 into 40, which is nothing but 1600. Therefore, when you pump, let us say 10 microampere current at the input, you will get 1600 into 10, 16,000 microampere, which is 16 milliampere. We can drive, our two-stage amplifier can drive 16 milliampere load. Very important, right? Having two-stage gain, which is current gain, which is 600, is also very high. Therefore, I can say your common emitter amplifier is also providing very good current gain. Not very good, it is providing good current gain. Overall, if you ask me what is power gain, if you ask me power gain is nothing but AB into AI. Therefore, what is AB into AI? Then if you calculate, you will get 16,000. What do you mean by 16,000? If you give, therefore, if you give, this is single stage, this is single stage, this is single stage power gain. Therefore, single stage power gain, which is 16,000, is too significant. Therefore, what does it mean? If your input signal power, if Pi is 1 milliwatt, then your output signal power P0 will be 16,000 milliwatt, it is 16 watt. Means, let us say this is what your audio amplifier, whatever signal I am speaking here, let us say if that is what is having 1 milliwatt of power, then it can drive 16 watt loudspeaker. It can drive 16 watt loudspeaker, because the common emitter amplifier is having power gain which is 16,000, that is too significant. Okay. Then if you speak with respect to audio amplifier, I think single stage amplifier, that is what is good enough, because you are having power gain. But if you want to design a generic amplifier like your op amp, where I want huge gain, therefore I'll use that op amp in many applications. Therefore, to get generic amplifiers like op amp, we want two stages. Therefore, two-stage gain, voltage gain and power gain, current gain, that is what is too significant. I can say your common emitter amplifier is passed with respect to voltage gain as well as current gain. Right? Therefore, everybody understood with respect to voltage gain and current gain. Now let's come back to Ri and R0. What is the significance of Ri and R0? Okay? Just to understand what is the significance of Ri and R0, can you just calculate AVS, which we already derived? We calculated AV and all, now calculate AVS, voltage gain with source resistance. Then you will understand the meaning of it, okay? Maybe if you want you can take this, then after that you calculate AVS. Therefore to understand the significance of Ri and R0, okay? Excuse me. I hope this is done. Now let's see the significance of Ri and R0, okay? Just to understand, okay, let us calculate. To calculate AVS. What is AVS? We know that AVS is equal to AV into Ri divided by Ri plus Rs, right? What is AB? 400, not magnitude, okay, minus 400. And what is Ri? We got 1 kilo ohm, we got, and 1 kilo ohm plus what is source resistance? 1 kilo ohm, right? Then what is this value? 1k by 2k, therefore you are getting minus 200. Therefore what is the meaning of minus 200? The real voltage gain with respect to actual source is minus 200. Even though your amplifier can have voltage gain of minus 400, but because of your RS or practical voltage source, the real voltage gain with respect to like V0 to Vs is minus 200. Half of the gain has gone because of RS, because of your practical voltage source, which is not acceptable. Your minus 400 gain we felt which is good, but now in the realistic scenario we are thinking that we get minus 400, but if you connect with practical current source, because we are always saying voltage gain with respect to what? V0 by Vi is what? Minus 400, but if you say V0 by Vs, which is nothing but your real voltage source, that is minus 200, which is not accepted, right? Therefore, let's see, I am saying that now I want to have, ultimately I don't know, ultimately I want to have Vi is equal to Vs. If I get Vi is equal to Vs, then whatever voltage gain I have, which is minus 400, I can get to the real voltage source also, right? Let's see, maybe a little bit theory, let's see how to get Vi is equal to Vs, then we will understand, okay? Therefore, this is what is minus 200, which is not acceptable. You can write it, right? Therefore, your AVS is now AV by 2, not acceptable. Means it's not wrong. The meaning of this is nothing but not acceptable. Not acceptable. half of the gain reduction is not acceptable. For that we need to do something. We are the designers. If you are the designer, if you are the design engineer, it is not allowed. AVS is equal to VAV by 2 is not allowed. Okay. Okay, now let me explain something, then I will come back to this once again. See, problem solving is over, but we should have the observations. These observations will give you, right, but not all the times we need to do the same observations. First time, because you are solving for the first time the problems, I am just giving you the information as well, the theory as well, right? Therefore, it is easy to explain later the remaining concepts. Okay, even though it is taking more time for the first problem, it's fine. We can continue faster for the later problems. Now, I want to model your amplifier something like this, right? Now, let us say this is what your voltage source. This is your voltage source. This is Vs and this is Rs. Okay. Now, this is what is connected to our amplifier. Let us say this is your Ri. Okay. Now, your amplifier is modeled with respect to amplifier. Then, whatever voltage we got. Therefore, tell me the amplifier input voltage we apply. This is nothing but your input voltage. Let us say this is Vi. Then, let me model in a different way. Instead of H parameter model, we can define the amplifier something like this also. Whatever input voltage which is what is applied, that is what is amplified by the gain, which is AV, which we already calculated, right? If you calculate the gain, then can I write like this? This is what is our voltage gain. Having voltage gain AV, and what signal it is amplifying? The signal which is what is present at the input of your amplifier. Therefore, I can take this as what? Now, and one more thing I want to explain, right? I want to explain is that to the external world, right, your amplifier, to the external world, your amplifier, let us say this is your RL, to the external world, your amplifier is nothing but voltage source. To the external world, your amplifier is voltage source. When I say voltage source, is your amplifier ideal amplifier? No, definitely it is practical amplifier. Then definitely it will have practically output impedance, which we already calculated already. Right? This is nothing but your R0. I'm just modeling like this. Your voltage amplifier can be modeled something like this, right? I'm speaking only with respect to voltage signals. Therefore, now if you see, if I model in this way, whatever signal which you are applying at the input of your amplifier, that is what is amplified by your voltage gain AV, let us say, then that signal you are trying to apply to your load. But remember, because of your output impedance, part of the output voltage which you got from your amplifier, that is dropped, only part of the signal, that is what is applied to your load, right? There also we can do some improvement, and here also we can do some improvement, because part of Vs is dropped across Rs, only part of the Vs is applied to your input of your amplifier. Whatever signal which is what is applied at the input of amplifier, that is what is amplified by your amplifier and then giving it to your load. Therefore, now Ri and R0 will come into picture, because they are interacting with real practical voltage source and interacting with real load. Therefore, definitely there is some loss because of Ri and R0 or because of Rs or RL. Okay, let's see. Now, what do you want? I want to have exact coupling. Exact coupling means I want Vi is equal to Vs. Then I can say there is no drop across Rs, right? Therefore, tell me to get right, Vi is equal to Vs. If I want to get Vi is equal to Vs, right, then there are two solutions. Number one, your Rs should be 0. Your Rs should be 0. Therefore, what do you mean by Rs is 0? I want ideal voltage source. I want ideal voltage source excitation to the amplifier. Therefore, it will amplify, right? That is the meaning of it. Now, 1 minute. Okay, now let us say there are two design engineers. Design engineer 1 is saying that my amplifier will give you maximum gain if you excite with ideal voltage source. And design engineer 2 is saying that my amplifier will give you maximum gain irrespective of the source. The source can be ideal, source can be practical. Which is better? Designer 2 or design 2 is better, right? Therefore, remember, source is not in your hand. Your source can be anything, but this is not the practical solution. We cannot say that Ri should be 0. That is not in your hand. As a designer, Ri is in your hand. You need to design such that you will get Vi is equal to Vs. Therefore, tell me for what value of Ri you will get Vi is equal to Vs? That is nothing but infinity. When Ri is infinity, right? Then open circuit, then current entering into your amplifier 0, then the drop across Rs 0, then it is open terminal case, your Vi will be equal to Vs. Therefore, your input impedance of your amplifier is in your hand because you are the design engineer. Therefore, your Ri should be infinity. This is what is the practical solution or practical requirement from your amplifier if you are designing the amplifier, right? But if you take common emitter amplifier, your input impedance is 1 kilo ohm, which is comparable to 1k or source resistance. That's why your gain minus 400 became minus 200. Okay, that is what is input side. Now let's come back to output side. You may ask, how did I represent or how did I model this like this, right? Remember, your amplifier is the voltage source for your load. Then I told you this is R0. We know R0 definition. What is R0 definition? Exclude the load, the impedance seen into output port when Vs is 0. When Vs is 0, Vi is 0. When Vi is 0, AV into Vi is 0. Short circuit. It is simply left with R0. That is what is R0, which is what is satisfied to definition. And we already calculated that R0, that you can use it here. Okay. Therefore, that's why I can represent it as a voltage source. Now output side. To get V0, whatever voltage which is what is amplified by your amplifier, that entire voltage I want to apply to your load. Therefore to get V0 is equal to AV into Vi. But that is not happening because of interaction between R0 and RL. And again there are two solutions. Number one, let us say there are again two design engineers. Design engineer 1 is saying that my amplifier will give you maximum gain. Let us say when RL is infinity. What do you mean by RL is infinity? When RL is infinity, open circuit, there is no current, there is no drop across R0, the center voltage will come to your output. Therefore, you are getting V0 is equal to AV into Vi. You will get maximum gain, right? Now, what is the meaning of it? Let us say design engineer 1 is saying that my amplifier will give you maximum gain if you don't connect any loudspeaker. Let us say this is audio amplifier. Don't connect any loudspeaker, you will get maximum sound or maximum gain. Is it practical? No. Therefore, your load is not in your hand, right? Your load is not in your hand. We cannot dictate anything about load. Load can be anything. As a design engineer, R0 is in your hand. Choose R0 or design R0 such that your V0 will be equal to AV into Vi. Therefore, can I say, tell me what should be R0 such that your V0 will be equal to AV into Vi? That is nothing but 0, ideally. Practically, this value should be very much less than your RL value. Therefore, it should be 0. As a designer, from your amplifier perspective, voltage amplifier perspective, I want output impedance to be 0. Therefore, tell me if you want to get maximum gain or if you want to have maximum available gain, your input impedance should be infinity, and to improve your voltage gain further, your output impedance should be 0. But if you take common emitter amplifier, what is input impedance? The input impedance is 1 kilo ohm, which is comparable to source resistance. Your output impedance is 52 kilo ohm, which is greater than 10 kilo ohm, greater than your load value. Take this, I'll give you some observations, then we can continue to next problem. Okay, this is what is the theory part. Because R0 in the case of common emitter amplifier is 52.5K, that's why voltage gain minus 400, else we would have got 10,000 etc. But why we got minus 400? That is because of R0. In the case of common emitter amplifier. Okay, done? Okay, now write down observations. Observations. Tell me what are the observations? See, now from now onwards I speak about Ri R0 first, not AV AI. Even though you have very good AV, very good AI, if you don't have Ri very high, R0 very low, we cannot utilize voltage gain, right? But for current gain, the requirements of Ri and R0 different. Remember, I am speaking about only voltage amplifier. Maybe just to add, whatever observations or whatever requirements we are speaking, that is only for voltage amplifier. Input is voltage, output is voltage. Therefore, it is only for voltage amplifier. When I say voltage amplifier, we will give voltage input and we will take voltage output. Therefore, this is what is our voltage amplifier. For current amplifier, again the requirements of Ri R0 they are different. I will explain all those things, but now it is voltage amplifier. As I told you, not all the things at the same time. Let's go one by one. This is for voltage amplifier, like voltage amplifier, current amplifier, transconductance amplifier, transresistance amplifier. Therefore, for voltage amplifier, these are the requirements. And I told ultimately I am looking for voltage gain and Ri and R0 for voltage amplifier. Okay, because your IC 741 is voltage amplifier and Ri and R0 for your IC 741, right? That's why we say if you take ideal op amp, input impedance is infinity, output impedance is 0. That is what we need. People designed and people got it. Okay. Okay, write down observations. The first observation, write down, we need Ri, the input impedance, very much greater than Rs. We need Ri very much greater than Rs. Ideally infinity, practically we want Ri value to be very high with respect to Rs, and R0 very much less than RL. Ideally we want R0 to be 0, or I can say it should be very much less than RL. This is practical condition. And R0 to be very much smaller than RL. We need Ri very much greater than Rs and R0 very much lesser than RL to get impedance matching, for voltage amplification. To get impedance matching for voltage amplification. Okay, you may think that what is the meaning of impedance matching? Maybe if you study from network analysis, what do you mean by impedance matching? Maximum power transfer. Here the impedance matching is not for maximum power transfer. Here the impedance matching is for maximum voltage transfer. Here the difference is maximum voltage transfer. That's why I told it is for voltage amplification. I am giving the condition for voltage amplification, not for maximum power transfer. For voltage amplification or for maximum voltage transfer, tell me if you want to get maximum voltage at the input side, I want VA to be equal to VS. The meaning of input impedance matching is nothing but if Ri is infinity, then people say that you have very good input impedance matching for voltage. Why? If Ri is infinity, Vi is matching to Vs. To match Vi to Vs, what is Ri? Therefore, you are getting matching. Therefore, matching for what? Vi to Vs, not for power. You understand the point? Therefore, don't think that Ri to be matched to Rs. Therefore, that is for maximum power transfer. But here I am speaking about maximum voltage transfer. If Ri is infinity, then Vi is matching to Vs. Therefore, that is for voltage amplification. Therefore, here the meaning of impedance matching is for maximum voltage transfer. Okay? We need Ri to be very much greater than Rs and R0 to be very much lesser than RL to get impedance matching for voltage amplification. But, write down, continuation. But, write down. But, from common emitter amplifier, Ri is not very much greater than Rs. Ri is not very much greater than Rs and R0 is not very much lesser than RL. Ri is not very much greater than Rs and R0 is not very much lesser than RL. Hence CE amplifier is not having impedance matching for voltage amplification. CE amplifier is not having impedance matching for voltage amplification. CE amplifier is not having impedance matching for voltage amplification. Just to prove that this is true, what is Ri value we got? Based on our values, 1 kilo ohm. What is Rs? 1 kilo ohm. Is 1 kilo ohm very much greater than 1 kilo ohm? No, that's why this is true. And what is R0 we got? We got 52.5. You can take it 52K. And then what is RL we got? 10K. Is 52K very much less than 10K? No, therefore it is not true. That's why there is no impedance matching for voltage amplification. Hence, there is no impedance matching from common emitter amplifier for voltage amplification. Okay? Second observation. This is first observation. This itself is the limitation. The observation itself is the limitation, right? Now, write down second observation. Second observation. What is second observation? Common emitter amplifier is providing very good voltage gain. Common emitter amplifier is providing very good voltage gain. In bracket, AB is equal to 400. In bracket, AB is equal to 400. Second observation. We have very good voltage gain. In bracket, AB is equal to 400. Very good voltage gain. In bracket, AB is equal to minus 400. But we are not able to utilize the available voltage gain. We are not able to utilize the available voltage gain. We are not able to utilize the available voltage gain and not able to improve due to not having impedance matching. 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 Therefore, you can write, therefore, that's what, right? Therefore, what is AVS? AVS is equal to minus 200. Therefore, AVS is equal to minus 200. Therefore, your 400 is becoming 200 because of not having impedance matching. This is related to input impedance. Therefore, because your input impedance 1K comparable, half of the drop is gone at the source, only half of the input is applied. Therefore, out of 400 we got only 200. And output impedance part we got minus 400. We would have got more if you have output impedance very less, but we don't have output impedance less, we have very high output impedance, then you have more drop across R0, only part of the signal you are applying to load, then overall we are getting, even you don't have very good output impedance, very good in the sense R0 is not very low and Ri is not very high, even though having all those limitations with respect to your output, we have still minus 200 voltage gain. This is what is our ultimate voltage gain which you are getting from your amplifier. That is what I want to say. What I want to say, because we don't have impedance matching, right? Due to which your common emitter amplifier is having the voltage gain minus 200 for the source of 1K and a load of 10K, right? For example, if it is having very good impedance matching both at input as well as output, maybe instead of AVS minus 200, it may be minus 2000 or minus 10,000, right? Why it is limited to only minus 200? Because of these limitations, which are nothing but input impedance matching and output impedance matching. I hope this is clear. Therefore, for voltage amplifier, remember, we want input impedance very high, we want output impedance very low. But we don't have that from common emitter amplifier. That's why your voltage gain we need to adjust with AVS minus 200. Else we would have got more and more voltage gain. Okay, fine. What if maybe we got voltage gain, right? At least we got 200. We should be happy with that. Okay. I hope this is done. Now I can say problem is over. Because we had observations and not at conclusion. Because if you want conclusion, we should compare with another configuration. Now we only covered common emitter amplifier. We should cover other configurations. Then based on the observations whatever we have, right, then we can have the conclusion also. I hope this is clear. Okay. Now we can solve the next problem. Maybe before going to next problem, again the session is not enough to proceed for the next problem. Let me stop now, then we will continue in the next session. Okay. This much analysis we need not do for remaining configurations are like for your MOSFET amplifiers and all, because for the first time we are seeing the amplifier and trying to understand what is voltage gain, what is current gain, and what is input impedance, what is output impedance, like significance of Ri, significance of R0 for voltage amplifier, right, etc. Therefore, it will take time, but as we continue, right, it will be faster. And one more point I want to tell, because now we understood the advantage of common emitter amplifier, which is nothing but very good voltage gain, very good current gain, but we are not able to utilize. That itself is the limitation because of not having proper impedance matching, which is Ri and R0. Okay, let me stop now.